Let's see a general recipe for Bootstrap first, and then we'll talk about the rationale and some applications. Our problem can be formulated as follows. Suppose x1, x2 all the way up to xn are IID samples from fx. Let t, which is equal to a function evaluated at the random samples, be a statistic. This statistic t can be an estimator for a parameter of interest theta, or it can be a test statistic. Like before, so like the case for Monte Carlo inference, we are interested in the sampling distribution of t. The sampling distribution of t can be useful for many things, such as standard error approximation of an estimator, establishing a confidence interval for theta, and doing hypothesis testing. However, unlike before, unlike the case of Monte Carlo inference, we do not know fx. This implies that we cannot draw random samples directly from fx. You should recall that in Monte Carlo simulations, in each replication, we draw n samples from the underlying distribution fx, and then we use the sample to calculate t. But that's not possible here because we don't know what exactly is fx. All we have is this random sample of size n. Our question is, how can we approximate the sampling distribution of t when we only have the n observed samples x1 all the way up to xn? So the bootstrap presents one method for estimating the distribution of t, ft, given our observed random sample x1 all the way up to xn. This is done by drawing bootstrap replications of the statistic t. Specifically, for each bootstrap replication, small b, ranging from 1 to large B, we want to draw n random samples with replacement from the observed sample x1 all the way up to xn, where each of these outcomes is associated with probability 1 over n. So essentially, we are drawing n random samples. We are resampling n random samples from the observed sample we have, which each outcome has equal probability of occurring. So the n random samples we draw with replacement from this set is going to be the beef bootstrap sample. And let's denote it by x1 of b all the way up to xn of b, where xi of b is a random sample from this set. Given our bootstrap sample, this thing, we can calculate the beef replicate of the statistic TB. And this is simply the t function evaluated at our bootstrap sample. It turns out that the empirical distribution of the TBs across the large B bootstrap replications, if we denote it by f hat of t, this f hat of t will approximate the sampling distribution of t, ft, which is the sampling distribution we are interested in, and we can use to do standard error approximation and all of those other good things. Let's see a toy example involving the LSAT exam. This example is described in the textbook, and it illustrates the idea of bootstrapping procedures. Later on, after seeing this example, you'll get an idea of how exactly this procedure is performed, and then we'll talk about why the f hat of t obtained this way can approximate ft later on. This example for LSAT, the law school admission test data, is available in requires using the Bootstrap R package. So there is a data set called law inside this R package that we will use. The code for this week's example are available in the examples week 7 R markdown file. Okay, So we'll start with installing and loading the Bootstrap R package. So if you haven't already, please install this Bootstrap R package. You can either do it in the bottom right corner inside RStudio, or you can say install.packages quote bootstrap inside your own console. We'll use two data sets inside this Bootstrap R package. One of them is called law. This contains a random sample of n equals 15 universities in the US from the universe, so a population of 82 USA law schools. So we have 15 random samples from the 82, and that's the data we have. So for this law data frame, it contains the 15 universities observations on two variables. The first variable is called LSAT, so we call it the X variable. So this is the average LSAT score for that particular law school. The other one is called GPA, so we denote it by Y, and this is the average undergrad GPA of individuals at that law school. So we mentioned that this law data set is a random sample, so a subset of a universe of 82 USA law schools. That's all of the law schools. So there's another data set containing all of the data on the 82 law schools in the US. So this data set is called Law 82, and this is the data for all 82 schools, and Law is a subset or a random sample of size 15 from this Law 82 data set. Just to give you an idea of what the dataset looks like, let's look at the first few rows of the law dataset. You can see that you get the LSAT scores for each of the 15 schools and the average GPA. So in this case, let's suppose our parameter of interest is rho, which is the population correlation between LSAT and GPA across the 82 schools. The true value of rho can be obtained by looking at the full data set of all 82 schools. So this is given by the correlation between the LSAT and GPA columns of the Law 82 data. And that's approximately equal to 0.76. However, let's suppose that we only have the law data with a subset of observations, so a total of 15 observations. An estimator, which is a statistic for rho, is the Pearson correlation, denoted by RXY, which is the correlation between LSAT and GPA inside the 15 universities. And that's equal to 0.77. So we're going to apply the bootstrapping procedures. Here, RXY is our statistic, in other words, our T. We will use Bootstrap to estimate the sampling distribution of RXY. What we will do is to do a total of 200 Bootstrap replications. For each of these replications, we will sample X1b, XYb, all the way up to XNB, YNB. So we draw the beef bootstrap sample of size n is equal to 15, with replacement from the original data of 15 rows. So X1, Y1, all the way up to X15, Y15. And then afterwards, we will compute the Pearson correlation of the beef bootstrap replicate. So let's denote that by RXY of B. So we'll end up with a total of 200 of these RXY of B's, which can help us approximate the sampling distribution of the Pearson correlation. So here's the R code for this. You can see it's quite short. First, say large B is 200, so we'll replicate this for 200 times. N is the number of rows of law, so we know this is equal to 15. R is the empty vector, or the zero vector, that we will use to store the RXY for each blue bootstrap replication. So for each bootstrap replication, we will first sample with replacement from the original data. So our original data are the 15 rows of x and y's. Instead of doing the x and y's here, we would just sample the indices, the row indices of that law data frame that we want for the bootstrap sample. So we will sample from 1 to n, and we'll draw with replacement a sample of size n. And then the correlation Rxyb of the beef bootstrap replicate will be given by the correlation between the lset variable of these particular rows that we have sampled with replacement in the beef replicate and the GPA variable for these particular indices. And the distribution of R here which is the vector of length 200, which contains our bootstrap replicates of Rxy, will approximate the sampling distribution of Rxy. So with these replicates, we have something that approximates the sampling distribution of Rxy. We can plot its histogram, which is given by histogram of R. If you want the density, you can do frequency equals false. And it shows you the distribution of the bootstrap samples across the 200 replications. Or we can also plot the empirical CDF. This is given by plot eCDF of R, CEX2, which essentially sets the size of the points over here. ZS equals 0.2, so I'm making the points showing up a little bit smaller than usual by default. So this is a empirical CDF for our R, the empirical estimate of the sampling distribution for the Pearson correlation. And we can also estimate its standard error. In this case, the bootstrap standard error for the Pearson correlation is simply given by the standard deviation of our bootstrap R's. So we can do SD of R, and that tells us that the standard error estimate based on the bootstrapping for the Pearson correlation is approximately 0.12.